NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, and welcome to another edition of the 2022 Von Karman Talks. I am Nikki Wyrick from JPL's Office of Communications and Education, and I will be your host for our topic this evening, a look at NASA's Earth System Observatory. NASA's Earth System Observatory will provide key information to guide efforts related to climate change, natural hazard mitigation, fighting forest fires, and improving real-time agricultural processes. Each uniquely designed satellite in the observatory will work in tandem to create a 3D holistic view of Earth from bedrock to atmosphere. Joining us as co-host this evening is Lindsay McLaurin, an outreach specialist from Earth Public Engagement. Hiya, Lindsay.
Hi, Nikki. Thank you so much for letting me join you tonight. And to everybody watching us from home, we're looking forward to having you be a part of tonight's conversation. So from wherever you're joining us, use the chat feature and one of our amazing social media specialists will pass along the questions to us. If you're having trouble finding the chat feature, refresh wherever you're joining and it should pop back up. Back to you, Nikki.
Awesome. Thank you so much, Lindsay. As always, if we run into any technical difficulties or small failures tonight, we ask for your patience and please stick with us. We'll get them sorted out as soon as we can. Our speaker this evening, Dr. Erika Podest, is a scientist with the Carbon Cycle and Ecosystems Group in JPL's Earth Science Division. Her research focuses on using Earth-observing satellites, particularly microwave sensors, to better understand how climate change is altering ecosystems. Hi, Erika.
Hi, Nikki. Great to be here.
We're so excited to have you. So, Erika, what is NASA currently doing to study planet Earth?
So, NASA is observing our planet from space in different ways. So, we can bring up the first video, and it shows NASA's Earth observing fleet. It currently has 23 Earth science observing missions in orbit, including 6 instruments on the International Space Station. And these different satellites and instruments measure the different components of our Earth's environment as related to the oceans, the atmosphere, and the land, the continents. And they measure things like sea level rise or atmospheric CO2 concentrations or soil moisture. And together, they provide a big picture perspective of our Earth as a system and help better understand our changing planet. The study of Earth from space started in the 1970s, and it has really revolutionized the way we study our planet because we can collect information with the same sensor and methods on a continuous basis over our entire planet, including very large areas or very remote areas.
So, over 20 missions. How do these missions study our planet?
We're looking at our planet in different ways, and these instruments use different technologies to measure specific parts of our planet. So let me first talk about the electromagnetic spectrum. If we could bring up the next image, please. We're making measurements in specific parts of the electromagnetic spectrum, and some sensors collect information about our planet using the optical portion of the spectrum. Those collected within, for example, the visible range of the optical portion are images similar to those that you see on Google Earth. There are other parts of the optical spectrum that are beyond what the human eye can see. And these data help identify things like specific types of plants, ocean color, the reflectivity of ice, or gases and aerosols in the atmosphere. Now, there are other sensors that measure the thermal energy or the heat that's emitted from the planet. And that helps, for example, to detect wildfires or to monitor the urban heat island effect. And then there are other sensors that make measurements in the microwave part of the spectrum, which can provide information about the atmosphere, such as precipitation, about the ocean, such as sea level height, and about the land surface, such as soil moisture. And then finally, there's another category of sensors that do not rely on measuring energy from a specific part of the electromagnetic spectrum, but they measure the gravitational pull of different parts of the Earth and provide information about mass gain or loss. And I'll talk about that a little bit further ahead. Now, one thing to note about the electromagnetic spectrum is that most of the energy on the spectrum is not visible to our eyes. And visible light is really just a small sliver of all of the energy that surrounds us. So these advanced sensors and instruments in space are providing information about things that we cannot see with our eyes.
I mean, it's just incredible to think of what we can already do and see with these instruments. What are NASA's next steps to better understanding our Earth?
So it's very exciting, the future, because NASA is planning to launch a new set of Earth-focused satellites before the end of the decade. And these are called the Earth System Observatory, also known as ESO, as shown in this next image. And the observatory will consist of 5 core satellites. And these satellites are going to provide key information to better understand things that affect our daily lives. For example, climate change, things like melting glaciers and ice sheets, warming oceans, or loss of biodiversity. Another example are disasters. We're already seeing a larger occurrence, a higher occurrence and intensity of disasters, wildfires, floods, droughts. And these new satellites will provide more precise information about these events that can help not only in mitigation strategies, but they can help inform disaster response and recovery efforts. A final example is agriculture. We'll be able to better inform on events that affect agricultural processes, such as droughts or diseased crops, and provide this information to relevant agencies so that they can implement better crop or water management strategies. So the Earth System Observatory, it builds on the capabilities of NASA's current 23 operating missions and past technologies as well. And each satellite will have a unique design and complement the other to create a 3D view of our planet, from the atmosphere to the surface to even what's underneath the surface. And so they'll not only help better understand the interactions between the atmosphere, the land, the oceans, the ice, but most importantly, how a change in one system influences another system.
The way these missions are going to work together, it sounds impressive. But where did this idea come from, and how will the focus of the Earth System Observatory be different from the current satellite fleet?
So there's something called the Earth Science Decatal Survey, and that survey identified 5 high-priority observing capabilities that were needed for future Earth missions. And this survey is undertaken by the scientific community every 10 years to look out 10 years or more into the future and really prioritize not only research areas, but observations and the notional missions to make those observations. And the last survey came out in 2017 and identified 5 observing capabilities as key observations for future satellite missions. So these are shown in the next video. And these are clouds, convection and precipitation, aerosols, mass change, surface biology and geology, and surface deformation and change. And these are critical components to measure in even greater detail than we've done in the past in order to better understand and predict the impacts of climate change and answer questions about our Earth system that we've never been able to answer before. So what is unique about the Earth System Observatory is that in the past, NASA missions have been built around the science question. In the case of the Earth System Observatory, It's being built not only to address science, but also applications and open science. And what do I mean by applications and open science? Applications refers to applying the data and the science for decision making. So for example, how can we use soil moisture information to inform farmers on when is the optimal time to plant their crops? And then open science is open sharing of data, methods, algorithms, software, results, just general knowledge, not only within the scientific community, but with the wider public as well.
So, this set of satellites will each have a different set of observing capabilities, like aerosols and clouds. Why is it important to understand aerosols and clouds?
So let's start with aerosols. They are one of the most important and still uncertain elements of the climate system. And a better understanding of aerosols and how they affect the global energy balance will help better understand climate variability and change, as well as air quality and weather. So aerosols are these small particles in the atmosphere that have a profound effect on our environment. And these particles can come from natural processes such as sea spray or dust or fires, but a large source comes from human activities, from fossil fuel burning. And aerosols influence climate and weather in two main ways. So first, they can reflect or absorb the sun's energy, influencing the temperature not only in the atmosphere, but on the surface as well. And then second, they can act as seeds for cloud formation, affecting the way that clouds form and the amount of rain that falls from those clouds. And clouds and rainfall can be quite different in polluted areas as opposed to clean areas. Aerosols are also pollutants, and they affect air quality, and if inhaled, some aerosols can have a harmful effect on people's health, especially the really tiny particles. So let's bring up the next animation, please. This animation shows the global distribution of aerosols in the second half of 2019. And note a couple of things. Note the dust blowing from West Africa across the Atlantic in brown. Note the smoke from wildfires, especially in Australia. This was a particularly intense wildfire season in Australia. And those are in red, and then sea salt in blue, and sulfates in purple, for example. And note how some of these aerosols are transported really long distances across our planet. And I'll focus on one of them, which is black carbon. It's also known as soot. And this is emitted from fires. And it can amplify warming because these particles are dark and they absorb the sun's energy. Another issue with these particles is that they get distributed around the planet, and you find them in the extreme latitudes, in the northern high latitudes, southern high latitudes. And what happens is they create this dark layer on top of either snow or ice, causing snow or ice to not only melt earlier, but melt faster. So a better understanding of how aerosols affect the global energy balance will help better predict climate change, for sure. And then clouds. They're one of the biggest challenges in the climate change puzzle. They're very dynamic, and they can either act like an umbrella by reflecting sunlight away from the planet's surface and back into space, or they can also act like an insulating blanket, so warming the Earth by preventing some of the heat in the atmosphere to escape back to space. And the blanket effect is especially noticeable during the winters, when cloudy nights are typically much warmer than cloud-free ones. And global warming is already causing and will continue to cause changes in the amount of cloud cover and the height and thickness of the clouds, shifting that balance between the umbrella and the blanket effects that clouds have. And small changes in cloud properties can have significant implications for global temperature. So better understanding clouds, convection, and precipitation helps tackle really the largest sources of uncertainty in future projections of climate change, and air quality forecasting, as well as prediction of severe weather. And the satellites of these, what we call the ACCP, so those are the aerosols, clouds, convection, and precipitation, will pick up where previous ones have left off, but with even more precise measurements. So for example, they'll be able to reach closer to the planet's surface to better quantify things like low and high cloud feedbacks or identify individual types of aerosols.
So the ACCP missions will give us an even clearer look, but can you tell us some of the other observing capabilities? For instance, why is it important to study surface biology and geology?
It's important because we want to know what is on the surface of the planet and understand how things are changing and how things react under certain conditions. JPL is already working on a satellite mission to measure surface biology and geology. And this mission will have a high-resolution imaging spectrometer that will subdivide reflected light into more than 400 wavelength channels across the visible and infrared. And it's going to be very sensitive to very specific features and characteristics of the surface. So can you please bring up the next slide? For example, by measuring the intensity of green chlorophyll from plants or detecting characteristics of a given disease on a plant, researchers will be able to evaluate the health of forested and agricultural ecosystems. Or by being able to identify invasive vegetation species, researchers can assess biodiversity loss in a given area. It'll also allow for mapping of different coral and algae species and characterize the reflectivity of snow and ice. And it'll also have a thermal radiometer. So I talked about the heat being emitted from the planet. And this thermal radiometer can be used for many different things, including detecting the temperature of leaves, for example. So when plants run short of water, their temperature changes, and scientists are able to identify if the vegetation is stressed. And in addition, thermal data can also provide information about heat from wildfires, volcanoes, and help keep track of warming ocean currents.
So, Erika, another focus you mentioned earlier is mass change. So, what can mass change tell us about Earth?
Mass change, as you know, has to do with large-scale changes and in mass. And that could be related to the loss of ice due to melting or to loss of water from underground aquifers due to increased consumptions or drought. So detecting mass change is important because it tells us that something significant is happening. And we know that some of these significant changes are not going to recover quickly from these huge losses of ice or water. And so we want to keep track of this large change and what is driving it. And NASA has been monitoring mass change with a series of satellite missions called GRACE and GRACE Follow-On. And these satellites were developed in collaboration between JPL and the German Space Agency and the Geo Research Center in Germany. So these missions measure the gravity field of the Earth, and that's shown in this next video. Note how that gravity field varies across the planet, and that depends on the mass. So areas that have like mountains or a lot of mass, the gravity field will be large in those areas. So to measure this from space, which is really amazing, the technology used is to have two satellites flying in tandem, about 220 kilometers apart. And these satellites calculate very small changes in the Earth's gravity by measuring differences in the distance between them, right, between those two satellites. So as the lead satellite passes over an area of Earth of slightly stronger gravity, so let's say it's passing over Greenland, which it has a large mass, it has kilometers of frozen ice. that satellite detects an increased gravitational pull. And so it'll speed up a little bit, just a little bit, and it'll increase that distance between the satellites is going to increase. And that is a very small distance, but it's measured by the satellite that's trailing it. And that distance is on the order of 1/10 of the width of a human hair. So it's really amazing technology. And if the Earth's mass, of course, doesn't change, then that gravitational pull would be the same for different areas of Earth. But when a large change occurs, then that gravitational pull changes. And this next video shows ice loss measured in Greenland and Antarctica on a monthly basis from 2002 to 2021, as measured with GRACE and GRACE follow-on. And we're talking about significant losses of ice, both in these giants of stored ice, on the order of 277 gigatons for Greenland per year, and 151 gigatons for Antarctica per year. And one thing to note is that these observations started in 2002. So recently, celebrating 20 years of gravity field measurements. Now, the Earth System Observatory mass change satellite will be a continuation of GRACE follow-on, but with improved capabilities to measure the Earth's gravitational field. And this information will, of course, continue to inform not only on the impacts of climate change on ice melt and their contribution to sea level rise, but to continue to support things like drought assessment and forecasting and associated planning of water resources.
Now we all know it is important to study clouds and aerosols, surface biology and geology, and mass change, but let's make sure we hit all 5 today. So, how is the Earth System Observatory going to study surface deformation and change?
So surface deformation refers to changes in the elevation of the surface. And the first satellite that will be launched as part of the Earth System Observatory will be able to measure surface deformation and change. And it's a JPL satellite called NISAR. And this satellite is actually a collaboration between NASA and the Indian Space Agency. So NISAR stands for NASA, ISRO, which is the Indian Space Agency, and SAR, the last 3 letters, stand for synthetic aperture radar, which is a type of instrument on the satellite. And this satellite is scheduled to be launched in 2024. So this next animation shows the deployment of NISAR and how that will look like once it's in space. So one thing about NISAR, I talked about synthetic aperture radar. It uses radar technology, which is analogous to an ultrasound. And the signal can penetrate through clouds, allowing us to observe the surface of the Earth regardless of almost any type of weather condition and regardless of whether it's day or night. So these type of measurements are really useful for areas that are continuously cloud covered, or areas in the high latitudes where it's often, or a large part of the year, it's dark. And by measuring, the sensor measures small changes in the signal received at different times. And we can measure, by measuring the small changes, we can measure displacement in the Earth's surface, believe it or not, on the order of centimeters. And this sort of information on a regular basis can help inform on many things. So the next slide, it shows an example of things that this type of information can be used for. In this case, identify the discharge and recharge of local groundwater. So this animation shows the Los Angeles Basin, and the color indicates the surface level of the basin, or the elevation of the surface going up and down as groundwater is extracted and recharged on a seasonal basis. So when groundwater is extracted from the basin, that surface sinks around 2 to 2.5 centimeters, which is indicated by the light and dark blue colors. And in the winter, when the groundwater is recharged due to people or naturally, then that surface rises on the order of 2 to 2.5 centimeters, or about 1 inch. And 1 inch, I just wanted to show you, it's about the diameter of a quarter, a U.S. quarter. A U.S. quarter, it's not quite 1 inch, but that's more or less what we're measuring in terms of the surface rising and the surface sinking in this case. So, and the rise of the surface is shown by the red and yellow colors. And as you can imagine, this type of measurements can be related to the motion, or can be used to study other things, such as the motion of the tectonic plates on the planet, on our planet, due to earthquakes, for example. Or we can look at motion of volcanoes as pressure around them builds up. Or it can be used to identify areas at risk for landslides when there are small changes or small movements in the surface that lead up to a large landslide. Or it can also be used to look at single glaciers and how they are changing. So in addition, through a different technique, these radar sensors can also measure changes in the land surface related to water, so surface water or soil moisture, and also to ecosystems like changes in biomass or agriculture or wetland ecosystems. So this type of information supports water and forest resources agencies, disaster management and response, or climate change mitigation strategies.
The observatory sounds like it will give us an even clearer picture of what's really going on with our planet. So tell us, why is this research so important to us?
It's important because it's a capability that helps keep us informed about what is happening. So understanding Earth processes and our changing planets help inform on mitigation and adaptation strategies and in disaster assessment and response. But our health is inextricably linked to the health of the planet. And ultimately, we need to be able to grow food, we need to be able to breathe clean air, and we need to be able to have access to fresh, clean water. So it's critical for us to know these things because we depend on them for our survival.
Okay, so we know this is important for understanding our planet, but how did you get involved in this and why is it important to you?
So I developed a deep love, connection, and curiosity for our natural environment from a very young age. I grew up in Panama, which is a country with just lush tropical rainforests, beautiful nature, and my family loved the outdoors. Every weekend, without exception pretty much, we were outdoors, either camping or fishing or hiking or just simply exploring. And a good part of my weekends were spent in a place called Gatun Lake. And this is a lake in the Panama Canal. It's a man-made lake made for the transit of ships from ocean to ocean. This is a pretty big lake. And in the first slide that you see some of the activities that I was involved with, exploring. And one of them is in a boat. So in this lake, there were many rivers and creeks that would flow into this lake. And the next slide shows a better picture of the boat and my parents in the boat. It was a small aluminum boat that my father had, and he would love to take us exploring up these small creeks and as far as he could. And he would then turn the motor off, and just within minutes, the forest would come alive. And these creeks were so small, they were covered by trees. And these are some of the most vivid memories I have of my early years. It was amazing, just the sounds of the forest and seeing small animals just come out. And really what I do now is an extension of what I did back then, which was observing nature. I do it now from a different perspective from space. But ultimately, this is important to me because every once in a while, I do close my eyes and I am transported to those places that were so special. And I just hope they never go away.
I mean, your connection to the subject and everything you told us tonight, this is all just amazing. I know the audience has got a ton of questions for us, so I want to take some time To do some Q&A, Lindsay, what are they asking out there tonight?
Thanks, Nikki. Erika, everyone is so engaged and excited to hear you talk about our Earth and the Earth System Observatory. So, Thomas from Facebook asked, which subject or specific topic do you find most important for the advancement of Earth surveys and technology? For example, environmental science, geology, or chemistry?
Wow, that's a great question from Thomas. I think that they are all important. I can't put my finger on a single thing because now our our natural environment and the study of our natural environment is so interdisciplinary, and even the studies I'm involved with require many different experts to tackle a given problem. And so I work with people that are biologists, ecologists, geologists, and 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 you need all of this expertise to really understand our planet.
Great. Thank you, Erika. Also coming from Facebook, Melanie would like to know, where do you see the most dramatic changes?
The northern high latitudes are really ground zero for climate change. Those areas are warming about twice as fast as the rest of the planet. So I would say the most dramatic changes are up north.
Great, thank you. Alyssa on LinkedIn asked, what will happen to the satellites currently collecting information once the new observations system is implemented?
Wow, that's a great question. So the satellites are built so that, first of all, there is some overlap between the current satellites and the new satellites, so you can cross calibrate. And also, they're built to have enough fuel to push them down to a lower orbit so that in a few years they just naturally burn up through the Earth's atmosphere. So rather than staying up there for tens and tens of years, depending on which orbit they are in, of course.
Thanks, Erika. Ben on LinkedIn would like to know, how long does it take to compile a 3D snapshot of the Earth in a moment of time using the information collected?
Wow. Okay, that's another really great question. So when you say 3D, so there's 3D from compiling information about the atmosphere and what I talked about the surface and underneath the surface. I'm not sure if you mean that, or if you mean like surface deformation, where we're kind of looking at the third dimension, right? This movement of the surface, and I'll refer to that. So that's done through a technique called interferometric synthetic aperture radar, and that takes quite a bit of processing. There's software out there to do it, and I think in a couple of minutes, once you have everything kind of processed, you can generate these what they're called interferograms in a couple of minutes. It's obviously going to depend on how many images you have and how large of an area you're looking at and what are the capabilities of your computer.
Great, thanks, Erika. User Satori Mystic on YouTube would like to know, when will we be able to see a visualization of the actions and reactions of aquifer systems, the effects of soil conditions, plant growth, and other such interrelated systems?
So you can already see the actions and reactions of aquifer systems. In fact, the GRACE and GRACE follow-on satellites have quite a bit of research. There's quite a body of research and results showing aquifer depletion in different parts of the world.
Great, thanks again, Erika. Sunji on LinkedIn asked, can we measure entropy to track how climate changes?
Can we measure entropy to measure how climate changes? That's a good question. So entropy would be the instability of things. So things going from something being homogeneous to inhomogeneous. And that would be different depending on what you're looking at. So I'm not sure I can answer that. I'll have to think about that one.
That's one of my favorite answers, the I'm not sure, because that's what scientists are asking every day. As Brian White always likes to say, that's the best question. The best answer is, I don't know, let me go find out. So this is going to be our last question of the evening. So Lindsay, last question for us.
Thanks, Nikki. So, Erika, Alyssa will bring us home from LinkedIn, and she wants to know, in your opinion, what is the most impressive observing capability for the new observation system, and what data are you most excited to get back?
Oh, wow. They're all amazing. All of the technology that's used by these different satellites, these new satellites, is amazing. However, my heart is close to NISAR because I am part of the NISAR science team. And so that's the one I am really most excited about.
I know NISAR is very near and dear to your heart, and we are all looking forward to it. So, unfortunately, that is all the time we have today for questions. I do want to thank our wonderful speaker, Dr. Erika Podest, for joining us to discuss the Earth System Observatory and sharing all of your wonderful insights. Also, thank you to our amazing questions co-host, Lindsay McLaurin, and everyone working behind the scenes to make this possible. To all of you watching, thank you for taking the time to join us every month. If you missed one or would like to revisit any of our Von Karman talks from the past 5 years, they are all available on JPL's YouTube page. And make sure to join us next month for New Star, Studying the Universe in X-ray. Stick around for a short video about the Earth System Observatory, and we will see you in May. Bye, everyone.
As NASA prepares to send humans to the Moon and Mars, and peer even deeper into the universe, we turn with a renewed focus to our home planet of Earth. The next generation of Earth science begins with the new Earth System Observatory. The core of the observatory is an array of 5 new satellite missions that will study the atmosphere, the ground, and even what's happening underneath the surface.
These spacecraft will look at the Earth, each one of them their own way, and will integrate all the data in a common approach.
Taken together as a single observatory, we will have a complete 3-dimensional understanding of our Earth systems, how they work together, how one change can influence another. It will watch our planet change, driving solutions for better living, managing water and food resources, predicting natural hazards, coping with sea level rise in coastal communities and heat islands in our cities.
Every 10 years, the best scientists in the United States and worldwide come together and create a strategy, the Decatal strategy, and it recommended that we build missions that together form an Earth System Observatory.
We're going to be looking at processes at the microphysical scale, at the large kind of convective scale, at the smaller scale in the oceans, and we're going to be investigating those, pulling that out, encapsulating that, putting that into weather models and climate models, and those are going to allow us to predict and project the future with far more confidence.
We can, from space, help farmers. We can help others that grow food around the Earth.
If there is an earthquake, we can get our models better, and from there we can predict better also in the future.
We can monitor fresh water both on the surface and underground to help water managers, both for communities as well as agriculture.
To build the observatory, we will expand our partnerships with commercial companies and international space agencies to take advantage of innovation and new technology.
We recognize, because of the global nature of the issues at hand, we want international partners to be part of that also. We're working together, and the science that we're doing has to serve all of us.
NISAR is our first major partnership with the Indian Space Agency in Earth science. It brings together 2 different kinds of radar systems that together we'll see changes in our Earth's surface that will help us predict natural hazards in the future.
The NISAR mission will measure changes in Earth's surface less than a centimeter across. It will measure the movement of glaciers and ice sheets, the dynamics of earthquakes and volcanoes, and changes in farmland.
We will observe the Earth every 12 days exactly at the right repeat pass orbit. We can study small changes in the Earth system sciences.
The Earth's climate is changing. We have documented the changes that we're seeing over the last few decades. We know that it's being driven by human activities, and it's absolutely essential that we continue to understand what's happening, what's changing, in order to better predict what's going to happen and perhaps help people make better choices.
Understanding how our planet and its climate are changing is the foundation for a more resilient and sustainable future. NASA's Earth System Observatory is the next step in this ongoing mission, a mission to the only planet you can call home.